Measurement of normal mode helical antenna in implantable application. Implantable application is known as implantable medical devices where it implants medical devices inside the human body through a medical procedure to observe health condition of a patient. Implantable antenna are used widely in a medical application. One of the application is to evaluate the temperature of cancer tissue located inside or outside of the patient body, and types of antenna depends on the location. Wireless Body Area Network (WBAN) is one of implanted application that is introduced to expand in the whole human body and connected through a wireless communication channel. The capsule-shaped device of size 11 mm x 20 cm provides visualization of a gastrointestinal (GI) tract and act as an image transmitter to a data recorder. There are few other examples of implantable medical devices such as a cardiac pacemaker, implantable cardioverter defibrillator (ICD), coronary stents, and small intestine endoscopy. Implantable radio wave devices must contain an implantable antenna in order to allow in-the-body communication. However, implantable antenna face more difficulty and challenges than wearable antenna for on-body communication due to complex human tissue condition, as a human body is said to be a lossy material because the performance of antenna is easily affected by the conductivity and permittivity. Since human body is lossy, radio wave degradation was very severe. Hence, radio wave devices need to be improved. This research would like to contribute to the development of wireless capsule endoscopy device, especially the antenna technology. Normal mode helical antenna (NMHA) is a promising candidate of a radio wave sensor implanted inside a human body for health monitoring system due to its high efficiency in small size. The target application of NMHA is in the wireless capsule (WCE), and it is expected to operate inside the human stomach. Human stomach is also surrounded by fat tissue. In this research, human fat tissue will be phantom used for the measurement. There are three main problems in this research. One of it is a fabrication of human body phantom. The correct chemical composition must be clarified due to the dielectric constant such as permittivity and conductivity, depending on the amount of the chemical powder used during the fabrication of human body phantom. Hence, each type of human body is different. Body tissue has varying dielectric properties. The fabrication must be also clarified. Secondly, permittivity and conductivity of fabricated phantom. The dielectric constant, permittivity and conductivity need to be measured once the fabrication of human body phantom is done. It is to ensure that the recommendation dielectric constant is met by the human body phantom at 402 MHz. Lastly, electromagnetic propagation in a phantom. As it operates, the antenna emits electromagnetic waves that are applied to the human body. The emission of electromagnetic propagation must be investigated. The objective of this study are to fabricate human fat phantom at 402 MHz to measure dielectric constants such as permittivity and conductivity of fabricated of human fat phantom at 402 MHz, and to fabricate NMHA with self-resonance, and lastly to measure the input impedance of NMHA between simulated and measured result. According to the research paper titled Implanted Antenna Inside a Human Body, Simulation Design and Characterization by J. Kim and Yahya Rahmat, the permittivity and conductivity for human fat phantom should gain 11.06 and 0.08. So based on the table, it can be summarized as a human body phantom can be fabricated by the commonly used in the critical parts such as stomach, liver, and fat. Next, what software that gonna be used and what its function. So, in this research study, there will be the electromagnetic EM simulation software that will be used in FECO. FECO is a computational EM software for 3D EM simulation developed by Alta Engineering. FECO uses method of 90 moment MOM integral formulation of Maxwell equation as a solving scheme, which subdivide the wire and the material component into smaller segments through machine. FECO is suitable for analysis of various kinds of antenna, which instant horn and aperture antenna, strip antenna, array antenna, helical antenna, and so on. FECO consists of three main parts, which is CAD FECO, Post FECO, and Edit FECO. CAD FECO is used to design the antenna environment and the antenna structure. And the right side is the example of designing antenna using CAD FECO. The table above shows the simulation parameter that have been set up in a FECO. There are few things need to be filled in, such as frequency, antenna structure, metallic wire, dielectric material, and mesh size. Whereas Post FECO provide the visualization of result in various forms, such as, for instance, the radiation pattern, near field and far field data, 2D result on Gaussian graph, Smith chart, or polar plot. And the right side is the simulation model of Nmha in a Fat Phantom designed by using Post FECO.
After completed in designing the simulation of FECO and data analysis, next I will proceed to the fabrication of human Fat Phantom.
Based on the picture on the left side, there are types of material and their amount. And the first one is polyethylene powder, 110 gram, xanthan gum, 8 gram, agar powder, 8 gram, and glycerin, 200 ml. The first step is weaving the chemical material according to the recipe. And the step 2 is put in agar and glycerin and dissolve it. Step 3, heat the solution with medium fire and stir it until the solution becomes transparent. Step 4, turn off the fire, put in the xanthan gum bit by bit and mix well. And step 5, pour polyethylene powder bit by bit and mix well. Step 6, transfer the solution into the desired phantom mold and let it cool and harden. The first picture shows the solution being heated, and the second picture is I put in the thickener, or known as a xanthan gum, and polyethylene powder bit by bit. And the last one is the mixing the chemical powder. Make sure all the chemical is mixed together. Next, I will proceed to the next fabrication, which is the fabrication of normal mode helical antenna. The fabrication process of Nmha is summarized in the following step, which is step 1, determine the dimension of Nmha for corresponding human Fat Phantom, including the number of turn, antenna diameter, and height of antenna. Circumference of the template is calculated and drawn according to the dimension on the piece of hard paper as shown in the figure on the right side. Roll the template that has been drawn into a cylinder as shown on the right side. Step 3, after the dimension is confirmed, use copper wire to coil around the cylinder according to the line drawn. And step 5, the center of the antenna is cut into half and attached to a iKohza cable by soldering them. After completed the fabrication of human Fat Phantom and Nmha, I need to do two types of measurement using vector network analyzer (VNA). And the first measurement is a measurement of dielectric constant of human Fat Phantom. Before proceed to more detail, calibration process need to be done. Calibration needs to be done following the manual before it starts measured. iKohza probe is used in this calibration, and the range of the frequency between 350 to 450 MHz needs to be set up. Then, calibration is performed step by step, which is measuring the open air, shorting block, and deionized water. If the permittivity of the ionized water is tested correctly, and finally it's considered the calibration process is successful. After the calibration process is completed, the probe is used again to measure the dielectric constant of Fat Phantom as shown in the figure. Base of the Fat Phantom is marked with a 5 point and used for measurement. The second measurement is the measurement of input impedance of Nmha inside human Fat Phantom. It also conducted using VNA. The first procedure is almost the same, which is need to do calibration. The purpose of calibration in this measurement is to ensure that the S parameter measurement is accurate according to the standard. In order to connect the balloon to the port cable of VNA is because to determine the suitable connector and need to connect the iKohza cable to the calibration kit. Calibration kit that are required are open, short, and load. After calibration process is done, the iKohza cable with the calibration kit is replaced with the iKohza cable with Nmha. Based on some research, the Nmha cannot direct touch to the Fat Phantom. Hence, plastics are needed to wrap around the Fat Phantom and Nmha. It is to ensure the minimum contact between Fat Phantom and Nmha. The Nmha is wrapped and placed in the middle of the Fat Phantom. Smith chart is chosen in order to read the measurement of input impedance. For the measuring of animation in Fat Phantom, 2 phantom are needed and hence there will be 10 measurement of point. The first picture shows the 5-point mark on the base of a phantom. Based on the measurement of dielectric constant, the average for the permittivity is 11.08 and the conductivity is 0.11. And the result for the measurement of dielectric constant of human fat phantom is 52.98 input impedance. Comparison between simulation and measured result. The Nmha should operate at the frequency of 550 MHz. The measured result obtained is 400 MHz and 52.98 ohm, which means the self-resonant frequency for the fabricated is 450. The different frequency of antenna might be deformed as bit as it is quite fragile and quite hard to solder it perfectly. Another reason might be the Fat Phantom hole to place the antenna is not in the middle position when poking. Conclusion, the objective of determining fabricated human Fat Phantom at 402 MHz measured dielectric constant permittivity and conductivity of fabricated human Fat Phantom at 402 MHz, fabricated Nmha with self-resonant, and lastly measured the input impedance of Nmha between simulated and measured result are achieved.